Okay, so with this we've come to the final part of the tutorial. I'll try to keep this last part brief and give a nice wrap up. So just to give you all a quick recap, Jose first walked you through the NOMAD website at large, after which we focused on this method section, and in particular the computational methods. Now, you might have noticed that we've actually skipped one subsection here for the density functional theory. As the veterans among you will know, this part has been there from the very beginning of the archive. And even when well established, we keep on maintaining these sections, further polishing and even extending them. That is because the way we look at and talk about data within the community keeps on evolving, as does the variety of users and their use cases. So the general layout of the side menu is that it allows you to narrow down the type of functional that you're looking for before then presenting you with additional parameters to fine-tune your choice. This filtering style starts out very general with Jacob's ladder, which got a bit of a touch-up. And below, you can then look up a concrete functional name. Now, you'll notice that some of these names, such as PVE, they pop up twice, once with the prefix C for correlation, and once with the prefix X for exchange. This is because at FAIRmat, we follow community standards as much as possible. And in this case, we went with the nomenclature set by the libxc that allows for an easy evaluation of a whole range of density functionals. I'll go more in depth here later on, but for now, this is just to explain that the libxc splits out the exchange and correlation parts whenever they appear separate terms within the density functional formulation. For those of you tackling semiconductors or insulators, likely you know that DFT fails pretty badly at capturing the qualitative behavior of these kinds of materials, of these classes, skewing mostly towards a more metallic description of the electron density. So two popular workarounds either see you add in or mixing in a Hartree-Fock exchange, which would be the hybrid functionals, or add in a penalty potential for off-site shell fill-ins, as with DFT plus U. Since both techniques mix in a correction, its strength has to be calibrated, and that is why we find each of these filters. Apart from that, they very much behave as you would expect these quantities to do. I think this for once is a filter that you can really tackle at as you would do on first sight. Let me maybe just point out that for the effective Hubbard term, this is very specific to Dudarev's implementation of DFT plus U. And there are other variations with their own parameters. You can find those under the data section of each entry. We're just presenting Dudarev here since it is by far the most popular implementation, and it rolls up several of the other parameters like U and J into it. Anyhow, if you're interested in insulators or semiconductors, you should really look out for these toggles, because once you have your material down, so once you have, like, as I showed before, your material selected, they can give you an overview of the ranges of values that other scientists have tried out. And it's often very interesting to see how the choice of value changes the properties. Lastly, there are some older, soon-to-be deprecated quantities. You can expect them to be vamped up and moved to their own sections in the near future, just as what we did with the basis sets on the precision. Now I want to switch up things a bit and dig a bit deeper in how we can refine the search for density functionals as we're currently doing with these upper two filters. So let me switch tabs here. So NOMAD has a very intertwined history with DFT. That is also why it features such a huge collection on the public website. Now, the stats that you were seeing before are only for the reprocessed fraction, but in total, we have close to 12 million DFT calculations, the vast majority of which are PBE. I don't think that this comes to anyone's surprise that PBE is featured so prominently, but it accounts up to 9 million entries. Now, this is great news for data scientists as it provides them with a wide sampling of the material space at basically the same accuracy, right? Because when you're building your model, you can't really start mixing in data that comes from different functionals now, can you? Still, there are use cases where this would be the goal to compare between different functionals, right? The first thing that comes to mind is benchmarking, but maybe a user says, I want to have the trade-off between a wide sampling and a better accuracy. Because let's face it, there is no single density functional that is a go-to for all properties, least of which PBE. It is well known that, for example, PBE sol and PBE mol will give you much better geometries for solids and molecules respectively. Then there's also the scan family, with R2scan in particular being very much preferred for energies, not to mention forces or densities and band gaps. So compared to, let's say, wave function methods or Green's function methods, the catch is that there isn't really a reference manual or a book that you can go and consult that will tell you which functional to use in which case, or that will kind of present to you all of the diversity and the functional landscape that is out there. This is because many functionals came out of separate undertakings with the eye on tackling specific problems rather than a coordinated kind of approach. So except for Jacob's ladder, which itself may be a bit too broad, there is no single framework theory that can hold all of the functionals out there. Essentially, you could say that we're dealing with a zoo. So the question that I want to present and address here is, how can we help users from different backgrounds navigate this landscape and pick out the functionals from the zoo that best align with their needs? Essentially, such a framework would live somewhere between the broad runs of the Jacob's ladder and the specificity of individual functional names. It would act as a kind of bridge, if you so will. So the way to go about this is start from the libxc, which we already use for the nomenclature, as I mentioned before. So libxc contains around 700 functionals, and it is basically a code library with a very wide adoption among app initial codes. This means that these codes, during the self-consistent cycle, when they're relaxing the electronic structure, can outsource the evaluation of the exchange correlation. So they can outsource that specific step, or at least the semi-local versions, to libxc. This does not mean that this is the only implementation that these codes have. Typically, they will also have their own internal evaluation of some density functionals, though it might not cover such a wide range as with libxc. The point for us here is that the libxc and some other similar libraries, they are code, not a database. So if we want to start formulating queries and start extracting knowledge from them, we first will have to verify them. And this is a really important point. The FAIR principles are not limited to raw data that you upload alone. In fact, when, for example, a vocabulary is FAIR, it basically has become an ontology. So by extension, this can also be applied to the knowledge within the field. And that's what we did here, focusing mostly on findability, since accessibility has already been covered. And then afterwards, once we can use queries and the like, we can start looking for insights, making information comparable and interoperable. So we ended up going with a graph-based paradigm, and I hope that by the end of it, I will have convinced you that this is indeed a sensible approach. So on the left-hand side, you have a first overview of what this would look like. Now, there are two things to note here. Firstly, we have a color coding that is applied in line with Jacob's ladder. This ladder is basically a hierarchy that classifies functionals by the amount of information that they ingest. And this is somewhat tied to the physics that each run can describe. In that sense, it should also provide you with better accuracy as you climb the ladder. Overall, this is true, yes, but when you go into some kind of niche or sub-pocket of materials, this might no longer be the case. It is not always a given that, for example, meta-GGA in each subset of materials will trump an LDA. So you have to be very careful there, and you will typically need some additional benchmarking. Still, it's good to keep this classification in mind via the color code here. Then the second aspect is that you have these clusters that are forming, with the one in the middle being obviously the most prominent one, but we also have smaller clusters down here as well. These are functionals where the libxc itself is telling us that they are composed by other functionals, essentially trying to capture the best of several worlds. That actually tells you a lot of what we are looking for, so it comes very close to our objective. But the problem is that this metric is quite sparse, so it can only carry us that far. As is, this landscape is quite unconnected and quite unstructured, so the question is, how do we extend it? Now, a first step would be to look at provenance. The libxc accounts for where these functionals come from. Typically, these will be publications or journal articles. We've added the references in light blue here, and there's about one for each functional, which is typically the one where the functional is first conceived. And in total, this means that we get around 700 papers. Now, what you see is that immediately, without doing anything else, you have this natural structure that comes out, describing almost an historical progress from these simpler LDA functionals at the bottom here to the more modern and much more complex hybrids up here. So what we are seeing is that the way the community thinks and talks about functionals at large, for the most part, aligns with Jacob's ladder. Of course, this can easily be pushed further. These articles themselves have other references, which we can also add. The combinatorics here will make this explode really quickly. If you just go one step further, you will get close to 6,000 papers. I'm not going to show you all of that here because it would just end up becoming one massive blue blur. Still, safe to say that this seems to be a sensible way to map out the landscape. I think we can all agree on that, right? So to further structure this, we're now going to apply our own systematics here via a clustering algorithm. There are several algorithms out there, but the one that is most popular is this Louvain clustering, because it manages to work with as much information of the graph as possible, while also being well balanced. Now, we apply Louvain here only to the references, and to make sure that it's operating on the same type of information. When these references belong to the same community, they are then connected to this pink node. Since we're more interested in the functionals rather than the references, I'll link the functionals here to the community nodes via their references and leave the latter out, just to have an easier time visualizing this. That basically then introduces or lays out this figure here on the left-hand side. And I think that we can all agree that this is indeed more structured. You can almost even pick out individual communities and start drawing borders, right? The big question now is, are these categories sensible? Do these clusters tell us anything about what is being put together? Can we, so to speak, put some kind of semantic label on top of each of these community nodes? Well, to answer that question, what we'd have to do is actually start evaluating all the references that make up an individual community. So start reading all of these blue nodes. Here I am showing you one such subpocket right now. And this one is one of the smaller communities because it only has 19 references. Don't forget, though, that in total we have close to 6,000, or actually 7,000, sorry, references. So it becomes a huge task to go through this manually. In other projects, such as the perovskite database project, the authors address this by basically crowdsourcing the extraction. In our case, we went with a more semi-manual approach by also relying on PageRank. Now, I'm sure that each and every one of you here is intimately familiar with PageRank, or at least you should be if you've ever Googled something. Indeed, PageRank was the original algorithm developed for the very first version of Google, that you can see here in the reference. And it was basically developed to support the Google search engine. Now, don't get me wrong, I'm not saying that this is still the current day implementation of the Google engine. Actually, I'm pretty sure that it isn't. But still, it helped spawn an entire new generation of search engines that nowadays we take for granted. Anyhow, since you're also familiar with it, you should understand that it basically gives you a ranked list of suggestions. In Google, these are websites best matching your query. Here, they are rather the most talked about publications. That is to say that if you were to start reading somewhere one of these references, and you just follow the citation tree for as long as your attention span lasts, the nodes with the highest rank are the references where you will most likely end up. It does not reflect anything on the relative quality of these references or the merit of the individual articles, but that's just fine for us. We are actually more interested in those most talked about papers because we assume that these will also reflect the common theme of a community. So let's try this out. Here you're seeing the PageRank results of the sub pocket that I was showing you on the previous slide. And let's do a little competition to see who's still awake. Let's see who can guess the overall theme of this cluster. I'll give you one hint. You only need the publication title here. And while some of you are looking into that, let me point out how there are many big names popping up in the author list. Now, that is because we are actually retrieving real classics in the field. I don't think that is too strange if you consider that for a moment, because indeed most classics are, classics are by definition the most talked about papers, right? Anyhow, what is most important for our intents and purposes is that the page rank here drops off very rapidly. This means that we can cap the amount of references that we read, and basically we then fall back onto a level where we can again apply a manual approach and manually vet these articles. So moving on, I'm now showing you again the full clustering, but with some additional borders that more clearly denote each of the communities, and also some labeling that we already started applying. This is still a work in progress though. Nonetheless, we can already glean a lot from the labels that we have here. So first of all, for those of you who guessed that the previous small community, the one here, was basically centered around Coulomb screening, congratulations. Moving on, I think there are some other very stellar examples of the power of this method. For example, we have a community here that contains all the two-dimensional functionals. Now, the functional dimensionality is actually tagged in the libxc, but it was not fed into the algorithm. Yet, it manages to capture all of them without an exception. This really perplexes me. Why does this work for the two-dimensional case, but not for the one-dimensional? To be honest, I'm not entirely sure, but my first guess would be that the red thread connecting all of these systems here, all of these functionals here are the systems on which they were tested. Surely you have some kind of image pop up, or we all have the same image pop up when I mentioned 2D materials, right? On the other side, then you have, for example, these kinetic density functionals that pop up as a separate community. And indeed, this is a theme that is a bit of a segue out of the typical exchange correlation physics that is described by most density functionals. And what is really amazing is that just as the theme stands separate, also this community stands separate from the rest. Vice versa, then we have groups that both tackle non-local interactions, but in different ways. And these end up still being connected via some kind of bridge. In this case, just you only need two functionals to move from one to the other community. So essentially, you can tell that the graph distance here is correlating with the thematic distance between communities. And this suggests that the theme is actually being extracted, meaning that the way we talk about functionals and the way we connect them to each other in our discussions is actually a very valuable metric, or at least when done at the community level. Now, I could keep going on and on, but I think I will just point out one more example just to give you really the full flavor of what is going on. And that would be GGA's Made Simple. So this was actually the first paper introducing, or the paper introducing PBE. And more importantly, actually the enhancement factor for correlation functionals. Now, you would assume PBE to have a huge community surrounding it, but actually it ends up being one of the smallest ones out there. This has everything to do with the Louvain algorithm itself. What it does is it namely measures modularity, which is a metric of the amount of information that you gain when associating a specific node to a community rather than having it be part of the graph at large. Now, because PBE is so omnipresent, and the same can be said for Pegasus 88 functional, there is really little information gained by saying that a functional is connected to PBE. Instead, it would be better to file them under a more specific category that narrows it down further. And it's this kind of behavior that leads me to call in Louvain clustering well-balanced. So up to now, I've heavily emphasized the power of clustering by reference. But is that all we can extract from the libxc? No, not quite. We can go a bit further. So the libxc devs, they understood that not each functional warrants its own implementation, but that rather many functionals share a common overarching formula, what I call a kernel here. Now, from the kernel's perspective, its functionals are just parameterizations of the same mathematical theme. That is not to make light of their differences, because different parameters do entail different densities and different potentials. And actually, oftentimes, the story behind how these parameters were obtained, let's say either from fitting or some kind of theoretical argument, is just as important as to which kernel they belong. So what we can do is take these functionals that surround a specific kernel and package them together even more specifically by linking them to common parameter values. So one example here would be, again, going with PBE sol, and let me see here, PBE mol. So you can tell that they actually both encode for the gamma and B parameters, but differ at the beta parameter, at least for the correlation part. And there's also the exchange where they will differ in another parameter. The point being that this seems to be a very interesting, potentially powerful tool, but can we incorporate this structure along with the reference-based approach that we were having before in a way that we can extend our current results? I'm not going to go too much into the technical details here, but suffice it to say that it requires projecting out both graphs together and then calibrating their relative strengths. Instead, I will just give you a teaser of what comes out of this marriage. So here you are seeing again a clustering. This time there are no borders applied, no labeling yet, because we haven't gotten around to a thorough analysis here. But still, what becomes apparent is that you have two levels of communities. So on the one hand, you will find these smaller communities with the same parameter values. Note that in this case, you will also have the same Jacob run, so the same run on the Jacob's ladder pop out in most cases, or maybe have some hybrids mixed in as well. And this makes sense since what this is basically telling us is that we have close to the same mathematical formula, so probably it's the same type of information being ingested. It's very sensible that we retrieve the same runs. But this is actually a very important feature to come out, because it means that now we are retrieving Jacob's ladder at large, but with a further narrowing down. And that's very important if we want to start bridging between Jacob's ladder and the individual functional names, so that we are in line with the ladder itself. Now, while we then have these smaller communities, they are all connected to this larger gray community node that is in line with what we established before with the references. So essentially, you will have some kind of overarching theme. You could consider this to be a research problem or research question. And essentially, each of these sub-pockets then are different ways of tackling the problem presented, which is, I mean, it's really amazing to me that we can get this kind of structure out of it. With that, we've come to the end of this presentation. Here I'm just showing you a quick overview slide. But there's one more point that I'd like to make today. And that is that I really want to reiterate that this is just a side project within FAIRmat. Obviously, you're looking for ways to incorporate it into NOMAD, which is and will always be our main product. Probably will enter there, as I mentioned several times, as a kind of bridge between Jacob's ladder and the exchange correlation search. However, this endeavor, in my opinion, also has value in of itself, as it addresses the way that we as a community understand and describe density functions. That is to say, FAIRmat has a wider scope than just NOMAD, and it can indeed accommodate endeavors that seek to stimulate other metadata research. Examples like this would also include the ontologies that my experimentalist colleagues are working on, and the construction of some and further enhancement of some specialized databases. Of course, we don't operate in a vacuum, and we are always very open and very happy to collaborate with the community and support community initiatives as well. What I'm just saying here is that we have this additional view or this larger scope, and I'm actually very curious to know what you think of these types of side projects. Do you see them having some kind of value to yourself and your research? Or would you prefer us to just stick to essentially maintaining and extending a highly automated repository? So I think that is enough food for thought. Thank you all for your attention, and I'll now be taking questions.